What's up, everybody? Hey, it's Dr. J, and what we doing today? Yo, we're still talking about chemistry. We're still talking about chemistry here. All right, that's all we're doing. So let's just dive straight into it. No time to waste. Dipole forces. Dipole forces. Okay, so far in this series, right, we've been talking about different types of intermolecular forces. Right, we covered London forces, and then we mentioned, right, there's four types of um, intermolecular forces. And once again, intermolecular forces is basically holding everything together, right? If you want to learn more about that or hear about that, check my other video um, to learn more about that. But today, oh yes, today we are talking about dipole forces. So before we get into that, one thing about dipole forces, as I mentioned before, this is between polar molecules. Now, a quick review, all right, and when we're talking about polar molecules have a permanent dipole. So these are extremely different from London forces when we cover that, right? London forces, that's a temporary dipole moment. Polar molecules have a permanent dipole moment, okay? Now, three things about that, right? Three points I just want to point out. Um, when we talk about polar molecules, in which we know that they're going to have a dipole moment, okay, but also the shape and bond polarity is also impacting that as well. Now let's look at this last one because they're permanent. Once again, these are permanent. There's always a present induced dipole. Okay, so because of that, we always have a dipole moment occurring with polar molecules. Okay, so because we have these permanent dipoles, okay, we know, right, there's a partial negative charge and there's a partial positive charge. So expect to see always some type of attraction between these molecules. Okay, so let's look at this point here. The permanent dipole adds to the attractive forces among the molecules, raising the boiling and melting points relative to nonpolar molecules of a similar size and shape. Okay, so let's talk about this. For example, let's look at this one. This is acetone. All right, so basically, what we see here, right? We got our carbon, but then we got this double bond here to an oxygen. Okay, so this is a polar molecule. And polar molecules always have a dipole moment. Dipole moment. So we're always going to have a partial positive and a partial negative charge. So in this case, right, and we can do a quick review, but if you want to learn more about polar molecules, let me know in the comments. I could definitely go over polar molecules, but you just got to let me know, right? So if you're not familiar with polar molecules, let me know. I could definitely do a whole video about polar molecules. But for now, I'm just going to give you the basics, right? Polar molecules, we know we're going to have a negative and positive charge. In this case, the negative charge is going to be on my more electron negative atom, which is oxygen, right? We got more electrons over there. So, right, it's going to give me that uh, negative charge. Compared to on the other end, right, more positive, right, not that many electrons, not that electron dense. So we got our positive end over here. And since this is a interaction between two molecules, okay, we got our other acetone over here. Same deal, right, more positive, more negative. Now, what we see is that dipole forces, this is only going to occur between polar molecules, right? Because once again, polar molecules have this dipole moment occurring. So my positive end will interact with my negative end, right? The negative end being oxygen, it's going to have this force uh, start to form between my partial positive end from my on this end of my molecule. Okay, so this is where we start to see these dipole forces start to form. Okay, and this is basically dipole forces. Okay, but on the other end, we also have ion dipole forces. Okay, so ion dipole forces are the same concept. We're looking at a some permanent dipole moments occurring. But here's the key word, it's an ion. Okay, so we're looking at ions here. Okay, so we look at my little definition here. The positive charge end of the polar molecules, for instance, water is attracted to the negative ions, and the negative charge end is attracted to positive ions. Okay, so basically, what does that mean, right? We have this ion-dipole interaction. So those dipole moments that are occurring on water, right, will be attracted to my lone ion. So for instance, let's say we got salt, we put salt in the water, okay? And what we're going to see, right, from our ion, our chlorine ion, for instance, because we know that in our solution, right, that these ions are going to be separate, okay? So if we look at chlorine, chlorine we know will have that negative charge, right? Negative charge. So remember, if we think about ions, we know that chlorine has a negative charge. It's a halogen, -1 charge. If you're not sure about that, that's Chem 1. Let me know in the comments. Can definitely go over that. But we got this negative charge here. Now, this ion dipole force, we're going to see this force start to be created by looking at our water, okay? So water, once again, water is a polar molecule. Polar molecule. So because it's a polar molecule, expect to see a partial positive end and a partial negative end. The partial negative end, we're looking at going to be on oxygen, but the partial positive is going to be on our hydrogens here. So because our hydrogen end will be the partial positive side, they're going to be attracted. So once again, these forces are just attractions, right? These are just attractions. So we're going to see attraction between our positive end and my negative end from our chlorine. So this is where our ion dipole force will start to begin, right? This is how they form. That partial positive end is attracted to this chlorine negative charge, okay? And we see this as they form here. But if we look on the other end, right, we got sodium, which is our cation. So cations, we know it's going to have a positive charge. So this positive charge, right, is attracted to still water, but notice how it's attracted to it. It's attracted to the negative end, opposite end of water. So now we got our cations interacting with our negative, our partial negative charge end of oxygen. So we see the ion dipole force form between the two here, okay? So that's the key difference between the ion dipole and then the dipole forces. Dipole, this is, that's a lot to say after a while. Dipole. Try to say that 3 times. That's a lot. But anywho, the dipole will be formed, right, with permanent dipoles because they're always going to be polar molecules, right? And that's the key thing we want to understand. Polar molecules can have dipole moments, as well as London forces, as we mentioned before. Ion dipole forces will only be between ions. So you don't have an ion, you do not have an ion dipole force. Okay, so you want to understand the difference between an ion dipole and a dipole. Okay, dipole. See, I tried to say it 3 times. It's crazy.